Okay, so hope this part is clear to all of you.
Yes, sir.
Okay, good. So let's look at some examples of the application of this. So now you have to work out these questions. Okay, so people just work out these questions. Send me the answers on the text. I will verify them. So you can do the full steps of the substitution and solve them, or you can also solve them by the direct formula type of method, like I've done for the exponential one in the above example. So far I've received only one answer from one person. I'm expecting all of you to solve these questions, please. Yes, very good, Anand, correct. Siddharth, let's check the answer of the first part. Others seem correct. Okay, I'm putting up the answers, the first three questions. Okay, so the integration of sine x is minus cos x. So now there's a coefficient 2 along with x, so that becomes like this. Okay. Similarly, this will become square root of 2x plus 1 plus c. This will become minus 1 by 3 into 3x plus 2.
Can you show the working of second and third?
What was the question, Vedad?
B and C.
Sorry, which one?
B and C.
I'll explain the questions. I'll do all of them. Okay, so for example, let's understand the first one, integration of sine 2x. Now we know that integration of sine x by formula is minus cos x. So therefore, integration of sine of any linear term is minus of cos of that linear term divided by a plus c. So just applying that over here. So in this case, a is equal to 2 and b is equal to 0. Okay, so this becomes and you can always check the answer by differentiating this. You can verify it. The differentiation of how much? So it's minus half into differentiation of cos, which is minus sine, but of 2x into 2, because you have to use the chain rule term here. That is sine 2x. So you can see it's correct. So similarly, now the second one, we know that integration of 1 upon square root x is integration of x to the power minus half. Okay, so it's 2 root x plus c. So therefore, integration of dx upon square root of any linear function will become 2 times square root of that linear function divided by the coefficient of x. You just use this over here. So it is 2 times square root of 2x plus 1, but divided by the coefficient of x, which is 2. So it comes out to be square root of. And similarly, you can verify the answer by. Okay, so basically, every time we are just using this kind of formula directly, there's no need to do the substitution steps. However, you can always also do this by substitution. Instead of using the formula, you can substitute 2x plus 1 as a dummy variable. And then you can see that dx by 2 will become dz. So the integration will become should in turn become x. Okay. So very similar method for the others. Okay. So just use this integral. So using this one, now we can see directly this one will become minus 1 upon 3x plus 2, but also divided by the coefficient of x. So that's how it becomes this. Okay. Let's come to the next part. Integration of tan 3x. So you have to keep this in mind that integration of tan x, remember the indefinite integration was ln of sec x plus c. So here this will become ln of sec 3x divided by 3. There's a 1 by 3 term here plus c. And likewise, let's come to the last one, which is this. Yeah, so interestingly, this can be written in two ways actually. So Caleb, your answer is correct. Okay, I'll explain how that answer also works out. So there are two things we can do here. One is that we can directly integrate this. So we know integration of dx by x is ln x plus c. So integration of a linear term in the denominator become ln of that linear term divided by a plus c. So using this formula directly, we can work it out that it is ln of 3x plus 6 divided by 3 plus c. Okay. But then we can additionally do one thing here. We can also, so this is fine on its own. This is the correct antiderivative because if you differentiate it, you will get this. Okay. But we can also show that this is 1 by 3 ln of, take the 3 common. Okay, plus c. Okay. Now we can use this property of log that ln a into b is equal to ln a plus ln b. So using this property, this is also equivalent to 1 by 3 ln of x plus 2 plus ln of 3 plus c. Okay. So further, this becomes 1 by 3 ln x plus 2 plus 1 by 3 ln 3 plus c. Now you notice here what is happening. This whole term is actually a constant. So you can absorb this within the constant. So this is equivalent to, so the constant of integration has an indefinite value. So any other constant term has to get absorbed into it. So this is also the answer. So interestingly, you'll see that if you differentiate this also, you will get this. If you differentiate this also, you will get this. So they are basically both equivalent to each other. So this kind of thing can be a little tricky sometimes, that you have to simplify the answer a little bit further if the option is not showing you this in the question. If none of the options is this, that means you have to simplify it a little bit further. Okay. Now another approach we could have taken here is we could have directly written the integration itself as this. Okay. And then we could have used this formula next. So we would have got 1 by 3 ln of x plus 2 plus c, which would have meant that it's the same answer as this. So in this case, this is also correct. Okay, there's nothing wrong with going with this method here. This is also correct. Okay, and if you simplify this further, then this answer is also correct using this method. Okay, so that means this answer and this answer are equivalent to each other. So that is where things can get a little bit tricky at the MCQ level, because you might have come to one answer, but you might have to simplify to another answer. So as always, these couple of properties of ln are pretty important. Okay. Ln AB is equal to ln A plus ln B. Similarly, ln A by B is ln A minus ln B. And ln of A to the power n is n times ln A. So these are important properties. Okay. So these few examples of simple integration by substitution of a linear term are clear to all of you. Please do let me know in case of any doubts in any of the steps. Okay, now from this we move on to a next type of substitution. Okay, so our next type of substitution is substitution of a function gx, okay, when the integration term contains g prime x. Okay, so let me explain this to you. So basically, if our integration is of this type, that it is integration of a composite function f of gx multiplied by another term which is derivative of g prime x. So for example, suppose we have like this, our integration is square root of sine x into cos x dx. So here you can see that if you take sine x as g, then derivative of sine x is cos x. Okay, and if you take f as the square root function, then f of gx is square root of gx. So that is square root of sine x. Okay, so therefore this integration can be treated as this type of functions integration. It is a composite function, is the product of two terms, root sin x into cos x. But in that, root sin x is a composite function, and cos x is the derivative of the inner function of the composite function. Okay, so it is a product of two things, a composite function. So f of gx is a composite function, and g prime x is the derivative of the inner function of the composite function, that is gx. So when this happens, okay, so for this type of integration, we use a substitution. Gx is substituted as a dummy variable. Okay, so then dz by dx is derivative of g. So we can then substitute g prime x into dx as dz. Okay, so these two things are then substituted in the integration, and the integration becomes a simple integration. It becomes fz dz. So next, substituting these two things. So the integration becomes integration of fz dz, which is suppose iz. So it becomes the antiderivative of gx. So we'll work out this example also and more examples how it works. But first, just make sure you understand the steps of the substitution. Then we'll come to the example and more examples. Okay, so just go through these steps carefully. Write down this method, then we'll discuss further. Okay, so now let's apply this to this particular example. So coming back to this example we had, square root of sin x multiplied by cos x. The cos x is outside the square root into dx. So here we recognize that if we take sin x as g, then cos is the derivative of this. Okay. So what we'll do is we'll substitute sin x as z. So dz by dx is differentiation of sin x, which we know to be cos x. Okay. So cos x into dx can be substituted as dz. So our integration therefore becomes this and this being substituted. It becomes integration of root z dz, which we know is 2 by 3 z to the power 3 by 2 plus c. So this integration becomes 2 by 3 sin x to the power 3 by 2 plus c. And now we can always verify this by differentiating the antiderivative. So if you differentiate 2 by 3 sin x to the power 3 by 2, so you'll take the constant 2 by 3 outside, then differentiate this by chain rule, so it will become something to the power 3 by 2. So it's that same thing into 3 by 2 to the power half into differentiation of sin x, which is cos x. So you can see that this is sin x to the power half into cos x, or root sin x into cos x. So it's exact like reverse of the integration that we did. It's like a reverse process of differentiation by chain rule. So just go through these steps and make sure you understand this. Let me know in case of any doubt.
Sir. Sir,
Yes.
we can also use direct formula, right, to solve this problem.
Direct formula in the sense that instead
To
of
the
substituting the z, you will just see it's square root of sine.
yes, sir.
Yeah, you can do that, but see, in lengthy questions, you are likely to make a mistake if you directly substitute. You understanding what?
Yes.
So it is better to do the steps of the substitution. If you feel confident on looking at the integration that you can do it directly, then it's okay. Especially some of them like exponential function and all will be easy to directly substitute.
Yes. Okay, sir.
Okay, so people, I'm hoping you're all clear with these steps then. So let's work out some examples. So this can be a bit of a tricky type of integration. Okay. So as I was telling Raghu, so all of you, the same thing, that at least in the beginning when you're getting used to this method, do the substitution steps, the dummy variable steps. Then as you get used to it, some of them you can skip the steps like you did for chain rule and differentiation. So let's look at some examples. Okay, so just work out these three questions. Let's do another one. Okay, so let's, for example, work out the first one. So what we can notice here is that the quantity inside the square root, this term, if you take this as gx, then g prime x is the term you have over here. Okay. So basically, this is an integration of this type. This of this type. Okay. And then you substitute this as z. So 2x plus 1 into dx will become dz. So this integration is becoming of the type dz by root z, which is 2 root z plus c. So the integration is 2 times square root of x square plus x plus 3 plus. And you can verify this, differentiate this, you will get the. Okay, so couple of you have made one mistake here. Okay, integration of dx by root x, that is integration of x to the power minus half. So it is, the power comes out to be half and not 2 by 3. So it's minus half plus 1. So it is 2 root x plus. Okay, so that's why this one is. Okay, very good. I'm getting correct answers now. Siddharth, Shivansh, Pratyush, Akshat. You just add the constant of integration, but yes. Shivansh, your third one is also correct. Good. See that this one, it works out to be e raised power x square plus c. This one works out to be natural log of x cube plus x square plus 2. Okay, so hoping all of you are clear with the methods up to C part. Okay. So for example, in B part, if you take x square as z, then 2x dx becomes dz. So the integral becomes e raised power z, like that. Okay. Similarly, in this part, if you take this term as z, so then its differentiation, which is 3x square plus 2x, becomes dz, right? So the integration becomes dz by z, which is ln z plus c. Okay. Now, similarly, let's come to the last one now. So if you see, if you take 1 plus sine square x as z, okay, then dz by dx is differentiation of 1 plus sine square x For that, you'll have to apply chain rule for sine square x. 2 sin x into cos x. So that shows us that the numerator that we have 2 sin x cos x into dx is nothing but dz. So this will be substituted and this will be substituted. So the integration will become square root of z in the denominator. That is again 2 times root z plus c. So that is equal to 2 times square root of 1 plus sine square x plus c. So this should be your answer in the last one. Yes, very good, Shivansh and Akshat. Both of you got this correct. So these type of questions, it's a little bit about observation. Okay. You have to see if the function follows that pattern. Okay. That there's a composite function, and also present in the integration is another term, which is the derivative of the inner function or the inner term of the composite, that is g prime x.
Can you scroll up a bit?
Sorry, ask again, beta, little bit louder.
So can you scroll a little up?
I couldn't hear you, beta. Little bit louder, please. Which one you asking?
So can you show the third part?
Third one, yeah. Okay. So like the C part. So in the C part, what you do is you substitute the denominator x cube plus x square plus 2sz. So then you'll see that dz by dx is 3x square plus 2x. Understood, no?
Yes.
Yeah, Adinath, I'll explain the second question also. So see what's happening in the second question is we have this integration 2x into e raised power x square dx. Okay. Now notice that if we substitute x square as z, then what is dz by dx? It's 2x. Okay. So in other words, if you think of x square as your gx, then you can think of e raised power x square as f of gx. This is e raised power gx. Okay. And 2x is nothing but g prime x. Okay. So the integration is of this type now. It's got this function, the composite one. Okay. multiplied by 2x. Okay. So once we know this, if we substitute this as z, then this becomes this whole term dz. So this becomes, so that's what we're doing here. Okay. So 2x dx becomes dz. So the integration, which is, I can also write it like this. This becomes e raised power z dz, which is equal to e raised power z plus c. So that is equal to e raised power x square. Yes. Okay, so hope it is clear now. So I'll just scroll up once more, go through all the parts and let me know if there's any doubt in any part, anyone. Right. So these examples are clear, I hope. So now we're basically done with all the techniques of integration. Okay. We'll do a bit more practice of definite integration with limits, and with that we will conclude our calculus portion, basic calculus portion. Okay. Now two special integrals to remember apart from this kind of substitution. Okay. So usage of trigonometry identities. So important trigonometric identities. This can be written as 2 cos square x minus 1, or it can also be written as 1 minus 2 sine square x. Okay. So in other words, using this identity, we can generate this one, that cos square x can be written as 1 plus cos 2x divided by 2, and sine square x can be written as 1 minus cos 2x divided by 2. Okay, so these are two important identities which we will use in integration. For example, we want to find sine square of pi by 8. So that is 1 plus cos pi by 4 by 2. It is. Oh, sorry. This is cos square. So this is an example of how we have used this identity for doing a calculation. But now we'll see how we use it in integration. So these identities, so integration of cos square x, we replace cos square x with 1 plus cos 2x. Okay. And then by 2, the whole thing by 2, and then split the integration by using property of integration. So this becomes x by 2, and integration of cos x, remember, is sine x. So integration of cos 2x is sine 2x by 2. With another half outside, it will become by 4 plus. Okay. So remember, integration of cos x is sine x. So integration of cos 2x will become sine 2x by 2 plus c. So this becomes the integration of cos square x. So this is an important integration to remember how to do this integration. You don't need to memorize this formula. What you need to do is remember that we use this identity for cos square x and we use this identity for sine square x. So now just write this down and then work out this one yourself. Integration of sine square x. Yes, Anand and Siddharth, very good. Siddharth, you have to just remember to add the So always remember to add the constant of integration, because in a subjective paper like your boards, unnecessarily you'll lose marks for skipping that. So remember these two integrals always. They are two important integrations that we'll use in a number of places in physics in the future. Okay. Hence, all the more important for us to.
Sir,
Yes.
we have to use only identities for integrating these two terms. We can't use any other method.
Any other method in the sense that, see, a substitution is not going to work over here. You're understanding now? Because you know, when you have cos square x, it's a composite function alone, no? The whole square of cos. There isn't the sine term along with it, no?
Yes, sir. Okay.
You understood? No?
Sir, whatever if it was tan square x, integration of tan square x.
Yeah, see, there are many integrations which are more complicated, okay, which we will not be covering at this stage in our basic calculus syllabus. Okay, there is a way of doing integration of tan square x also. You know, it involves a bit more complication. Like, I don't know if you have done these kind of identities yet, like cos 2x written in terms of tan x. Have you seen this?
Yes.
Yes, sir.
Yes, sir.
Something like this can be used, or there are other techniques also. But what I'm saying now, like integration by substitution and by identities is a very wide subject in maths. And when you come to advanced calculus in 12th, you'll learn many more techniques than what we are learning here. But here we are doing few basic ones which we require in physics. Okay, so the idea is we just about do enough so that you will not have difficulty at the physics problem solving level. Okay. And of course, when it comes to integration, there is another issue that, you know, there are certain functions which are actually non-integrable even. Antiderivative cannot be calculated for them. So it's a little bit more complicated in that sense than differentiation. Any function can be differentiated at the end of the day, and you'll see that the techniques we've learned in differentiation are more than enough to deal with any situation in differentiation. But the same cannot be said about integration. It's little bit more complicated. But in physics, we will come across only limited types of problems, and the techniques that we have learned here are more than sufficient to deal with those kind of applications. Okay. Now let's come back to definite integration. And we've learned about definite integration in the last lecture, but let's look at some application examples. So what we saw is that if we are integrating a function with some limits like this, or we can also express it as x equal to a to x equal to b. So this symbol represents the definite integration of the function fx from lower limit x equal to a to upper limit x equal to b. And what this operation gives us is, it gives us a value. Instead of an antiderivative, it gives us a value, and that value is equal to what? It is the area under the curve. Is the area under the graph of y is equal to fx in between the limits. So let's say this represents a graph of y is equal to fx, and these 2 points represent x equal to a and x equal to b. So then between these limits, okay, the graph encloses a certain amount of area. So this is the area we're talking about. This area. Okay. Now, of course, there is also the matter of how the calculation of this is done. So the calculation of this is done as we first calculate the antiderivative by indefinite integration, and on that we substitute the limits. So it becomes the value of ix at the upper limit minus the value of ix at the lower limit. So this kind of symbol with a bar with the 2 limits put is just to show that this is the antiderivative of fx. Okay, and on that antiderivative we are substituting the limits and subtracting the values. So as a very simple example, integration of x square from x equal to 0 to x equal to 1. So first thing we need to do is calculate the antiderivative, which is x cubed by 3. And then on that we need to put the limits 0 to 1. So the upper limit will become 1 by 3 plus c. The lower limit will become just c. So c cancels out and we get a definite value. So we get a value. Now what this value represents? It represents the area from x equal to 0 to x equal to 1 under the graph of y is equal to x square. So it represents this kind of area now. So we are familiar with the parabolic graph of y is equal to x square. So if let's say this point is x equal to 1, then this area now is represented by this. Okay, so let's do some examples. Now, this example will also explain a certain point to us over here. Integration of sin x from 0 to pi versus integration of sin x from pi to 2 pi, and integration of cos x from 0 to pi by 2, and integration of cos x from 0 to pi. Just work out these 4 values and we'll then interpret them on the graph also and see that they represent something important. Yeah, so Anand, to answer your question, if we have something like this, let's say this sine square x, then we'll just write it as this. Okay. And then put the limits after integrating. So this is the indefinite integration is, as we saw. Now on this we'll put the limits. So upper limit will become pi by 2 plus cos 2 pi, which is 1, plus c. Lower limit will become 0 plus cos 0 by 4, that's 1 by 4. So we get
Would be x by 2 minus cos 2x by 4.
Yeah. Sorry, wait. It is minus sine 2x by 4. So the value will come pi by 2 only, but slightly different for the indefinite integration. Okay. Sine square is 1 plus cos 2x, no, by 2.
So I guess 1.
It's minus. Yeah. Also in the integration, there will be a sine term. So this integration will be this minus sine 2x by 4, right? Okay, so this makes things even simpler. So the upper limit will become pi by 2 minus sine 2 pi. So that's 0. Okay. Plus c, and the lower limit is 0 plus 0 plus c. Okay, so this becomes pi by 2.
Got it, sir.
Yeah. So eventually we'll see like how to deal with substitution or identity type of integrations with limits also. But let's start with like basic ones. Okay. So like this one, you have to just see that integration of sine x is minus cos x. So in this now you have to just put the limits. See what value you will get on putting the limits. So this question is to show you that it's very tricky sometimes to get the substitution of limits correctly. Okay. When we do this, I'll show you that this will actually come out to be 2. Oh, sorry. Yeah, 2. So let's understand why it will come out to be 2. So this indefinite integration is the easy part. Now, when we put the limits, the upper limit will be minus cos pi. Okay. And we can leave out writing the c also. Just for completeness, I'm writing right now, but it's not required really. Minus of minus cos 0 plus c. C anyway cancels out. Okay. Now the important thing is, remember, the value of cos pi is how much? It's minus 1. And the value of cos 0 is 1. So it is in fact 1 plus 1, and that's how it comes out to be. So it's very easy to make a mistake. Okay. But has to be very careful about this thing. And just to understand how this comes out to be 2, or at least just to justify that it should come out as a positive quantity, just visualize the graph of sin x. It's like this. In one single cycle, looks like this. So you'll see something interesting here, that not only this graph shows you why this total area should be positive, it will also show you that integration of sin x, if you do from 0 to pi by 2, it will be exactly the same as integration of sin x from pi by 2 to pi, because these two are cut in equal halves. They're mirror images of each other, which is equal to 1. So you can do this calculation separately in this way also and show it. And that's why from 0 to pi, when we do it, it becomes 1 plus 1, 2. Okay. But likewise, yeah, sorry.
So what will be the unit?
What is the unit? Here we will write it as unitless because y and x are both numbers, but it's whatever unit square. You understanding? So if x is in millimeters and y is in millimeters, then it's millimeter square. Or if x is in centimeters, y is in centimeters, so it's in centimeter square. But here we'll take x and y just as unitless numbers for the moment. Okay.
Sir, cos pi is 1 or minus 1?
Sorry, come
Cos
again.
pi.
Cos?
Cos pi is 1, I think so.
No, cos pi is minus 1 beta. Cos is negative 9, the second quadrant, remember?
Yes, sir.
Just visualize your vector. No? So component wise, if you visualize, no? See, the easiest way to remember your
Yes, sir.
trigonometry in 4 quadrants, no? Is always remember it this way, that think of a unit vector like a cap, which is rotated through an angle theta. So its x component is nothing but cos theta, and its y component is nothing but sin theta. Then it becomes very easy to visualize all this, that when it's in the second quadrant, the x component is negative, but y component is positive. Like that third quadrant and fourth quadrant. Okay, so now I think all of you would have worked out this second part. You should be getting 0, right?
Yes, sir.
Now, what is the justification of getting this as 0? I mean, it's okay calculation wise, but now you can see why it's coming as 0, because this area here is cancelling this area. What actually happens is, if you integrate sin x from pi to 3 pi by 2, you will get minus 1. And same thing when you integrate it from 3 pi by 2 to 2 pi, that will also be equal to minus 1. Okay. So that is why ultimately your integration of sin x from, for example, pi to 2 pi will be minus 2. Okay. And that is why ultimately, oh sorry, pi to 2 pi, this is minus 2. This will be minus 2. Whereas if you were to integrate from 0 to 2 pi for the full cycle, you will see you'll get it as 0. Because this and this will cancel each other. So same way you put the limits here, you'll understand why this comes out to be. So limits are pi to 2 pi. So if you do pi to 2 pi here, you'll get minus cos pi minus of minus cos pi. So get this kind of term. So this substitutions of limits can be a bit of a tricky business. Okay, one has to be very careful about algebraic signs and all. Yeah, so I'll just verify the answers for you. That's correct. This one will be 1 and this one will be 0. So these two integrals will also show us a symmetry between the two graphs. Now remember, integration of cos x is sin x. So this one is easy enough, sin pi by 2 minus sin 0. So also, if you not just the cos graph itself, but if you also compare it with the sine graph, see the interesting symmetry that you get. So this is your cos x graph. So you can see that this area is coming out to be 1, but this area here will come out to be -1. And the shape is exactly symmetrical to the sine curve. Only the sine curve is shifted in comparison. So if you were to like draw the whole graph, not just from 0 to pi by 2 or 0 to 2 pi, to understand how they are actually the same shape, it is just shifted. Same wave shape. Okay, so that's why these areas are all symmetrical. You see these areas cancel each other. So what this also ultimately shows us that when we calculate area under a curve using this, gives us area with algebraic sign. Positive for above the x-axis and negative for below the x-axis. Okay, so hope this was clear to all of you. So people, with this we come to a conclusion of our basic calculus section. We will keep one more session for discussion of doubts and more example questions and all. But with this, you have all the techniques and methods required for solving anything to do with application of calculus in physics in future, as well as completing all the problems from the module and worksheets and everything in this section. So we are now ready to proceed to the next chapter, which will be kinematics. Okay. And as we get into kinematics, I will also be referring you to some additional books apart from the module. But of course, we will start with questions from the module and worksheets in kinematics also. So that's it for today, people. Thanks for attending and wish you all the best. Have a nice day.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Yes, sir.
Bye, people.
Thanks, sir.